get more as we get more spacecraft, and we get constellations, and we get small sats and CubeSats, and the data are available in real time or near real time, the old dichotomy of high spatial, low temporal is kind of disappearing, right? But for a long time it was that. You know, we used high spatial, low temporal to do proof of concept studies and detailed analysis. But if we wanted to monitor volcanoes and how eruptions change in intensity over time, we couldn't use those data because we didn't get them frequently enough. So instead, we had to use low spatial but high temporal resolution data like GOES, AVHRR, ATSR, MODIS, VIIRS, and into the future VIIRS. So, okay. So people just, sorry, Ryan, can you just confirm you saw that slide change? I'm on sharing, right?
Yes, we saw it.
Yeah. So low spatial but high temporal resolution are the basis for the space-based thermal eruption detection and monitoring systems. And the reason is what I'm going to describe here. So, and again, these curves, you've seen these a couple of times now. You know, if you're interested in this kind of work, try and produce these curves, because the curves that I'm showing you on the left basically tell you almost everything you need to know about thermal remote sensing of active volcanoes. And by playing with those numbers, you can prove to yourself anything you might like to prove. So we're going to refer to them again. This is the summit craters of Mount Etna as they existed in 1996, right? You'll see the scale here, 0 to 400 meters. Okay. This is a photograph of the Volcanova, this vent in the Volcanova, taken in September 97. That was the second time I went to Etna. Now this vent is about 30 meters in diameter. Okay. Each of these craters, well, that crater had a vent smaller than that, and then that crater had a vent slightly large, southeast crater had a vent slightly larger than that, and this one was quiet at the time. But at that time, there were just 3 vents at the summit of Mount Etna, one at 30 meters, and then the others at about 10 meters in diameter. So one here, and one here. Now, this is 400 meters. If we double that, this area is kind of one MODIS pixel, right? It's just one 1 kilometer pixel. So these 3 tiny little sources of radiance were all contained within 1 pixel. These are ATSR brightness temperature pixel maps acquired of Etna the very night that we were up there watching this, making measurements at this crater. 3.7 microns, the mid-wave infrared, and then 11 microns, the long-wave infrared. Okay. So in terms of low spatial resolution data, most of the time people don't like using low spatial resolution data because you think you can't resolve the thing that you want to resolve because it's much smaller than the size of the pixel. Right, so somebody just said they're studying fluvial channels. Now you probably use Landsat or Iconus or something like that to do that, because the size of the channels you care about is much smaller than the size of the pixel, is much smaller than 10 meters or something. You couldn't use GOES data or ASTA data or AVHRR data or MODIS data to study those kind of things because they would be subpixel in size. That doesn't stop us using low spatial resolution data to map volcanic hotspots. Because even though they're far smaller than the size of the pixel, the amount of radiance they radiate because they are so hot means that when you mix that radiance with the radiance from the ground around it, the energy measured at the scale of the pixel is still very, very high. Okay, so we'll look at these 2 graphs here. Again, curve 4 is land at this temperature, I don't know, 15 degrees C. So the land surrounding this vent is at 15 degrees C. Okay, so that would give us the black curve here, curve number 4. Now if I take, and that might be this pixel here, so this is down on the flanks of Mount Etna, so I just get that value. If I then add a small hotspot, I get curve number 7. So if I take something at 1000 degrees C, about 30 meters in diameter, and I add it to a pixel, so let's say 300K here, and then I add something this size to a 1 kilometer pixel, I get this green curve. Okay, because go back to the last presentation, it's the mixture of something small and hot plus something large and cool. And if I mix those 2 things, I get one of these bimodal mixed Planck curves. Okay. curve number 7. So this in a 1 kilometer pixel will give me the green curve. The same 1 kilometer pixel without this will give me the black curve. Now in a remote sensing data set, to detect this feature, what I'm going to do is I'm going to say, well, I've got a huge image which has 1,000 pixels in one dimension and 2,000 pixels in the other. What I want to do is write an algorithm which goes and looks at each of those pixels and decides whether it thinks it contains something hot. And if it does, record its details. If it doesn't, just move on to the next pixel and just repeat. Okay. So how am I going to do that? Well, I have to look at a wavelength where my target is separable from the background. So curve 4 is my background, curve 7 is my target, right? If I look in the long wave infrared, the green and the black curves overlap, right? Now what this tells me is this thing is, even though it's very hot, it's so small. So when I compute that mixed spectrum, I find that at this wavelength, it doesn't change the radiance very much. So it's very, very hard for me to distinguish the green curve from the black curve, right? They virtually have the same value in terms of radiance. And this is shown here. This is the 11 micron brightness temperature recorded for the summit of Mount Etna when this thing was up there. And you'll see I'm measuring the background temperature of the volcano, and I can see a little bit, there's a little bump in the middle right there. But it'd be very hard for me to write an algorithm that would identify that pixel against the background, okay? Because it really isn't very separable. And this graph just shows you why that is. So let's look at the graph again. If I look in the mid-wave infrared part of the spectrum, so 4 microns, I find that the background is radiating less than 1 radiance unit. The pixel containing the hot thing is radiating 10 radiance units, right? So this feature should be easily separable in a low spatial resolution image if I acquire that image at 4 microns, right? Because I have way more signal to detect it, right? I have big separation between curve 4 and curve 7, which means it's easier. Even if I add noise to these curves, I should still be able to tell that they're different curves, which means it should be easy for me to write an algorithm which separates one from the other. That's the basis of any detection algorithm, right? You're trying to isolate signal above clutter, signal above clutter. And then if I look at 4 microns, this is the 4 micron image of the same area at the same time. I find that it would be really easy for me to write an algorithm which identified these pixels and separated them from the background, right? And the reason is in this graph. I have way more radiance at 4 microns than I do at 11 microns to distinguish the pixel containing the lava from the surrounding pixels which don't contain the lava. Now I get even more separation at 1.6 microns, right? The reason I don't use 1.6 microns is because a couple of things. During the day, you can't use it. So remember, during the day, I have reflected light, these gray curves. So during the day, I find that at 1.6 microns, the noise contamination of reflected light is almost equal to my thermal signal. So I can't use it. If I have a sensor that acquires low resolution nighttime 1.6 micron data, then I can certainly use the shortwave infrared channel. The problem is most sensors don't. So ATSR and ATSR2, they used to acquire 1.6 micron data at night. And it was really easy to identify volcanic hotspots because you'd have a black image with a couple of white pixels in the middle. So it was just dead easy. MODIS doesn't acquire nighttime data routinely. VIIRS doesn't acquire nighttime 1.6 micron data routinely. Basically because volcano remote sensing is kind of a minority sport. So if you were to acquire global nighttime 1.6 micron data, that would be a huge data volume to downlink, store on the spacecraft, downlink, a huge data volume to archive. And they just worked out there aren't enough people who want to use it. And the cost of doing it isn't worth it. So when we're doing low spatial but high temporal resolution volcano monitoring or eruption detection, we don't use 1.6 micron data, even though it could be better during the night. We basically use 4 micron data is the main data set that we're going to use. And these maps and this graph shows you why. Okay. And just for some illustrative numbers, if I take my thermally homogeneous pixel at 300K, where it's just filled, this is background lava at 300K, At 11 microns, the radiance is 9.5, and at 4 microns, the radiance is 0.4. So you could just see that off this graph as well. If I add a small hot thing at 850 Kelvin, which occupies 0.05% of the pixel, you'll see the radiance at 11 microns barely changes. It goes up from 9.5 to 9.6. It barely changes. But the radiance at 4 microns goes up from 0.4 to 1.3. It triples. It goes from here up to here, right? So that's why we use 4 micron data. If there's something small and hot in a large pixel, you'll see a big signal at this wavelength, not such a big signal at this wavelength, and that will allow us to develop an algorithm which will help us isolate or segment these pixels, these 4 pixels, from within a million other pixels in the image. Okay. So just to show you some examples, I'll just go through these quite quickly. So here, reflected light curves on the left, and then we have, you see this pixel here, we have no lava in it, it's just ground at 300 degrees C, Kelvin, sorry, and we get that curve. I'll add a small hot thing. Now that's what the combined radiance curve looks like. So I've added something at 1300 Kelvin, which occupies 0.01% of the pixel. You'll see we get no separation at 11 microns. We get a little separation at 4 microns, and we get a big separation in the short wave, but we can't use that during the day because it's swamped by reflected light. So let's just keep adding 1%, 0.1%, 1%, 5%. So as the size of the hotspot grows, I get, eventually I get separation at 11 microns, but I get big separation at 4 microns, okay? If I'm looking at something hot at 1300 degrees Kelvin. So in low spatial resolution data, active lava is really, really easy to detect, okay? Because at 4 microns, whether it's by night or by day, you get huge separation. Just look at this. This is orders of magnitude separation between the signal and the clutter, okay? I will point out, during the night, you can ignore these curves because you just have emission. During the day, the Earth's surface does reflect light at 4 microns. Okay, so you do, during daytime, if you look at 4 microns, you do have a reflected light contamination. But if we just draw a line from here, we see that the radiance is, 0.7 clutter, 0.7 noise from reflected light, whereas it might be 100. So, the noise associated with reflected sunlight is a really small percentage of the signal. Okay. So in low spatial resolution data, active lava is dead easy to detect. It's so simple, it's embarrassing. So if we look at low temperature things like fumarole fields, so exactly the same thing, but now I'm just going to add a small cool thing to the pixel. 0.1%. So I've added a tiny fumarole field, which occupies 0.01% of the pixel, and it has a temperature of 100 degrees C higher than the background. You'll see the red curve lies on top of the blue curve. I would not be able to distinguish that pixel in a low resolution satellite image at any wavelength. If I make it 1% of the pixel, I still can't distinguish that fumarole field, right? Because the red curve just lies on top of the blue curve. Again, you can compute all these curves using the equations that I'll give you in these slides. If I make it 10% of the pixel, now I'm getting some separation, right? But in reality, I'm going to have noise on each of these. I'm going to have error bars or uncertainty bars on each of these curves associated with my emissivity correction and also my atmospheric correction. So again, I'm going to be challenged to distinguish the red curve from the blue curve, the lava pixel from the non-lava pixel. If I make it fill 25% of the pixel, again, this is a log scale, but you can draw some lines across here. I'm starting to get separation. The point of this is if you just run through those slides once I've sent it to you, active lava, dead easy to detect in low spatial resolution data. Geothermal anomalies, hydrothermal anomalies are much, much harder to detect because you just don't get the same separation in any of these wavelengths. So if you're looking for this one pixel in an image which contains 1 million pixels, you have to write an algorithm which successfully identifies this curve and separates it from this curve in the presence of noise sources, which may include emissivity, atmospheric correction, and then also this solar heating component that I mentioned earlier in the day. And that's much, much more of a challenge. So I'll just whistle through a few contextual. So I've included some algorithms here. There are a ton of algorithms. You should just search out the papers. You can use a multiband contextual hotspot detection algorithm. So This might be kind of Andy Harris's VAST algorithm, Louis Giglio, the Modis Fire algorithm. Basically, the way these things work are, you take an image, this is Mount Etna, and you have a kernel, right, which you just roam around the image. You just roam it around the image in order. And then you look at the brightness temperature, so you convert radiance to temperature using the equations I've already shown you. And you compute the temperature for each pixel in this 9 kernel box. And you compare it with the pixel in the middle. Okay? And you look to see whether the temperature of the pixel in the middle is significantly different to the temperature, the average temperature of the pixels around it, right? If we look at 12 microns, we compute the 12 micron brightness temperature and the 4 micron brightness temperature. You'll see that at 12 microns, I can't detect the active lava, right? But at 4 microns, eventually, this kernel is going to land on this pixel. And when it does it, it's going to say, well, wow, that value is way higher than the surrounding values. Okay? But you'll see we have background variation, right? There are gradients in here which are nothing to do with the temperature of the active, with the active lava. They're due to the temperature of the volcano surface, which we don't care about. The way we get around this is we subtract this temperature from this temperature, which produces this temperature, which is a thing called DeltaT in the literature. So what DeltaT does is it basically suppresses variations due to the background. So if we look at the 4 micron and the 12 micron is really just telling us about the temperature of the background. So we have a pixel with a small hotspot, but because of the reasons I showed you on the last couple of curves, the 11 micron isn't really responding to it. So just this curve, right? We don't get much separation here. Let's look at this, right? This is a small hotspot. We really don't get much separation at 12 microns, okay? So when we roam our kernel around the image, when we hit the summit, you know, the summit's here, but we don't really see the hot lava. What 12 is measuring is the temperature of the ground around the lava. At 4 microns, we see the lava, right? But you'll see this staircase feature here and here. We still see that in the 4 micron data, right? Because at 4 microns, we're still measuring the temperature of the background, right? We're still getting radiance associated with the background temperature. So what we do is we subtract this from this and we get this. And if you see with the DeltaT, basically what it does is it suppresses variations in background. So this is like this with this subtracted from it. And you'll see the staircase features have gone and the surrounding is flat. And we've just isolated the radiance associated with the active lava within the summit craters of Mount Etna. Okay, so this is called a multiband contextual hotspot detection algorithm. You basically roam this kernel around every area of the image, and then you compute the 4 micron and the 12 micron brightness temperature. And you basically say, well, if the 4 micron brightness temperature is hotter than the average of its surroundings, plus some estimate of variance or noise, and the DeltaT is greater than the background, plus some estimate of the variance in terms of standard deviation, then this pixel contains a hotspot. Okay, so that's how they all work. You know, there are various traps and various nuances, but they all basically work like that, right? So that's a contextual hotspot detection algorithm. If you look at Lewis's paper, 2003, you'll find this. If you look at Andy Harris's paper from 1997, his VAST algorithm, you'll find this. If you look at his GOES paper, Andy's GOES paper from 2001 in IGRS, you'll find this. They all work in the same way. So Modvalk is a multi-band point operation algorithm. This is a point operation, so it's computationally very efficient. It uses relatively few mathematical operations. When we were writing it, we were told we couldn't use more than 5 because at the time, I don't know, NASA was running 486s over at Goddard, so we couldn't use up too many computing resources. So we had to design an algorithm which was a point operation, and it had to use relatively few mathematical operations, and this is what we came up with. Basically what we do is we compute this normalized ratio value, This allows us to separate out these white pixels from the background. And in terms of histogram, if I compute this NTI value for every pixel in this MODIS image, right, I find that most of the pixels form this distribution here, right? They have an NTI value of between -1 and -0.85. If I zoom into the tail, I find that the pixels that contain the active lava have NTI values which form the tail of this distribution. So what we did with Modvalk was we established a threshold value to distinguish the pixels we cared about from the pixels we did not, and that's how Modvalk worked. So if NTI exceeds -0.8, it's a hotspot. If it's less, it doesn't. And then this is an example of, for this particular image, NTI identifies the pixels in a red box, but it kind of missed. You know, if you were an interpreter, you might look at these pixels and say, well, there's something in there. That was one of these pixels in here. We didn't get it. Something in there. That's one of these pixels in here. We didn't get it. So with any hotspot detection algorithm, there's always a threshold involved, whether you establish it statistically or you just establish it as a value. You have millions of pixels in the image and you only care about 4 or 5. You have to establish some kind of threshold to distinguish the 4 or 5 you care about from the millions that you don't. And in establishing that threshold, you're basically trying to minimize the number of false positives whilst maximizing the number of positives. And every algorithm has that kind of threshold. You know, if you try and maximize the number of detections, you will get more false positives. If you're too conservative and you really minimize false positives, you will miss positive detections. There's just no way around it, and that's the same in any field of pattern recognition or image segmentation or target detection. You're always faced with the same problem. These algorithms just use different ways to try and do it. There are time series based algorithms. So Nicola Pagola and Tramatoli, they've done some of this stuff. These kind of algorithms work by, this is a stack of images of the Big Island of Hawaii taken on multiple days, right? So what they do is say, well, we co-register these images, and then we're going to look at each pixel in that stack, and we're going to compute the mean and standard deviation. And we're going to try and exclude clouds, which is very hard, but we're going to try and exclude clouds. And what we're going to try and do is once we stack these up and calculated the mean radiance for each pixel, we can end up with a map that looks like this, which is the mean radiance for each square kilometer of this image over a certain period of time. And then they also compute the standard deviation as some metric of variance. And then what they do is say, well, this encompasses the average natural behavior of the Earth's surface in the absence of a lava flow. So then they say, well, when a new image comes in, we will take the radiance for each pixel and we will compare it with our reference value. And if it is within 3 standard deviations of the reference value, we're going to say that the ground at that time is behaving normally and there's no thermal anomaly. If a lava flow appears here, then that pixel will have a much higher radiance. And when you compare that area of ground at that time to the way it's historically behaved in the past, you will find that the radiance is outside of that 3 standard deviation limit and it's anomalous. And in that way, you can flag it as a hotspot and a thermal anomaly. So that's a time series based algorithm. John Dean also published a time series based algorithm. That was in geology in 2000. It was John Dean, Ken Dean, and Kevin Engel. So that's another time series based approach. We're developing a new time series based approach, which we're going to implement on vias. So when MODIS dies, we're going to basically apply Modvalk to vias, and we're going to have a global vias algorithm, which will use a time series based approach, but it won't use the mean, it will use the maximum, and we'll have some other methods in there to try and tailor thresholds on a global basis to improve their sensitivity. So basically that's how I haven't delved too deeply into that. You know, if you look at that paper and that paper and that paper, and I'll send some others, you'll be able, there are 3 ways of detecting hotspots in low resolution data. Those are the 3 methods. They're pretty simple on the surface. They just vary in the intricacies, and you'll be able to work out how they work. So I'll send them some references for that. So let's say you've detected an eruption. So you found a white pixel, right? Now what do you do with it? Well, you know, we want to derive other things. Part of the beauty of a time series is we can monitor changes over time, right? And we know volcanoes change in their intensity quite quickly on scales of hours to weeks to days to months. So the fact that we have a high resolution detection, a low resolution thermal detection at a volcano, and because we have a high temporal resolution, we can make the measurement several hours later or a day later. We can build up time series that look like this one on the top left here, right? So this is just, all I've done here is summed the 4 micron radiance detected from each pixel that Modvalk detected on each of the days between January and April 2006. So this is really easy. I mean, you do this in Excel for Augustine volcano. On the bottom is the RSAM, so the seismic amplitude measurement made at that volcano at the same time. And you'll see they map onto each other really quite well. So what can you do once you've detected the radiance from a volcano over time in a low spatial resolution data? Well, you can just add up the radiance values, and that's a good proxy for the intensity of the eruption and how it varies through time. So this might be enough for you. You might just be interested in looking at plots like this to work out when the activity is escalating and when it's de-escalating, escalating and de-escalating. So that's really easy to generate. You can estimate lava effusion rates. So again, here are some papers at the bottom that you can see how this has worked. So the way this works is basically we take an image like this, and using this equation, which is described in this paper, we work out the area of the lava at each point in time during the eruption. The area that a lava flow covers is proportional to the rate at which it comes out of the ground. So the quicker it flows out of the hole in the ground, the larger the area it covers before it solidifies and stops. It's no more complicated than that. So we can convert maps of radiance, look at each pixel, compute the radiance for each pixel, convert it to an area, find an area for each point in time, compute those areas over time, convert them to effusion rate, and in that way, we can estimate the lava effusion rate during lava flow forming eruptions. You know, read these papers for how it works. One of my recent PhD students did an accuracy estimate of how well this measurement works, and it works okay. So these are the literature values for these lava flows. So based on Landsat measurements or geodetic measurements, you know, like actual measurements of flow volume. And then the triangles and the crosses are estimates of the area derived from satellite data made using the method of Diego Coppola and Andy Harris from MODIS data. So what Estelle did was she took this method, their methods, these data, computed an upper estimate for the area by integrating the green curve, a lower estimate for the lava volume by integrating the blue curve, and then she plotted on the black curve to see how well the satellite method worked. You know, the good news is that the final flow volume falls within the bounds of the satellite estimates, but you'll see this is a log scale. So there's quite a lot of uncertainty. And Diego's values are systematically higher than Andy's values, basically because he uses a different assumption in the way he converts from radiance to effusion rate. So it works, but there are relatively large uncertainties. One thing Andrea Stefke did, if you estimate the effusion rate from a volcano over time, you can integrate that to work out the volume of lava erupted at the surface. She then looked at gas measurements to work out the volume of magma which actually arrived at shallow levels and degassed, right? And she then compared the difference. So basically, if 10 cubic kilometers arrives near the surface and degasses, but only 8 cubic kilometers, only 8, is erupted on the surface, then you know that 2 cubic kilometers was stored as hyperbysal intrusions, shallow intrusions. If everything that arises at shallow levels is erupted, you know that there was no shallow storage. So by comparing thermal remote sensing estimates of lava effusion rate with gas remote sensing estimates of the amount of lava which arrive at shallow levels, you can work out something about the partitioning of surface and subsurface magma partitioning. So Andy Harris published a paper about this in 1998, and Andrea published a paper about this in 2011. So that's something else you can do. You can drive lava flow simulations. So this is something that I did a while ago. So all I did here was take a lava flow, a numerical lava flow simulation model, which required effusion rate as an input. I just derived the effusion rate from the satellite data, and then took that effusion rate and used it to derive the numerical prediction. Because the effusion rate changes dramatically during an eruption, this chart here is effusion rate during the Etna eruption of 91-93, computed from satellite data many, many times. So you can see it peaked at 25, it was about 7, average value of about 7, and then the eruption ended here. But during the first month of the eruption, all I did was feed each successive satellite-derived effusion rate into the model to predict the flow length. And then these are maps of the actual flow length, and you can see it did quite a good job of predicting the flow length as I varied the effusion rate based on the satellite measurement. So I drove the model using the satellite data. You can predict the end of eruptions to a certain extent. So this is something one of my students did a few years ago. Basically, we compute these effusion rate time series from the satellite data. When the effusion rate drops to 0, by definition, the eruption has ended, right? So we look for this peak in the effusion rate. We build a time series. MODIS goes over. We estimate an eruption rate. We compute it. Once we've identified this turning point, we're on this downward waning flow phase of the eruption. So when we identify this, which is this point, as soon as we have another measurement the next day, we can then extrapolate that to 0 and predict the end, right? We can predict when the effusion rate hits 0. Now you find, based on 2 measurements, you don't get a very good prediction. But as we move through time and we add more and more measurements, we find that eventually the difference between the predicted end and the actual end decreases. And eventually we predict the end quite well. And we can do that quite early in the eruption. So this was very simple, and this was something that we could do based in real time based on the satellite data. You can do some time series analysis. So this is just, this was some wavelet analysis that I did from Modvalk derived time series. The problem with this is really we don't have long enough time series to do this type of analysis with enough measurements in it. So, if you're familiar with this work, basically you can't trust anything which is in this pale region because you're getting towards the edge of the data set. I found some evidence for periodicity at Mount Etna and Heard Island and Shiveluch, but most volcanoes didn't show any evidence for periodicity. You've got to be careful with these data because satellite orbits are not random, they are entirely predictable. So I remember reviewing a paper one time where somebody had suggested that they saw a 2-day periodicity in thermal output from these volcanoes based on MODIS time series. That was entirely fictitious. The orbit of MODIS is effectively 2 days. It's a 48-hour repeat at the equator. So if you apply one of these spectral analysis to MODIS data, you will find a 2-day periodicity. And if you try and write a Nature paper about how all those volcanoes vary on a 2-day timescale, you will be proving that satellite orbits are regular and nothing else. So be careful when you apply those kind of measurements. Okay, I'll finish there and take some questions.
Okay, great. Thank you so much. We'll see if we have any questions. And while you guys are coming up with your questions, I've just posted in the chat the link or the survey for session 4. So if you could please complete that, and that's part of the participation. If you're interested in certification, but also just feedback on the session, we'd very much appreciate that.
So I saw a couple of questions. Rate of flow, to a certain extent you can compute rate of flow, but remember, from a low spatial resolution data set, but remember your pixels are a kilometer, so the best you can do is a kilometer. If you stack images over time, you can do one of those super resolution type things and slightly, fake higher resolution, but rate of flow is limited by the resolution of the data. So this is why Ryan could do a really good job of it during the Kilauea eruption a couple of years ago, because he had drone images many, many times. So he could give you the rate of flow in, very, very precisely. You couldn't do the same thing from satellite data. when we predict the lava flow, what kind of things do we have to consider? I think viscosity. So viscosity is very, very important. So if you look at lava flow simulation papers, so if you look at, I'll put some references down for you because I can't remember the examples. Miyamoto and Sasaki, Andy. Basically, the way these simulations work is you take a pixel and you have an effusion rate and you fill the pixel with lava at a certain temperature. So if you imagine your pixel is 10 meters by 10 meters and your lava flow is 100 meters, is at 1 meter thick, then you have 100 cubic meters of lava, right, at the eruption temperature. So if that is in a period of 1 second, you have an effusion rate of 100 cubic meters per second. If you double it, the lava is 2 meters thick, 10 by 10, and you have an effusion rate of 200 cubic meters per second. The way they work is they say, well, okay, in a time increment, so say it's a second, I work out the radiant heat loss from the flow surface and the convective heat loss, et cetera, and I cool it. I then work out how much energy I've lost, and I adjust the internal temperature because I've lost some energy, right? So now the internal temperature of that lava is no longer 1,000 degrees C, it's 998 or something because you've lost some energy. So what they do is they recompute using temperature viscosity relationships and temperature yield strength relationships. They recompute what the viscosity and yield strength is, right? And then they work out, is it still runny enough to fall downhill to the next cell, right? If it is, some of the lava falls downhill in the DEM to the next cell. And then you just repeat this thing. You compute the energy lost by cooling. You work out how much energy you lost. You recompute the temperature. And then because viscosity increases as temperature decreases, the viscosity goes up, right? And it becomes more sticky. And eventually you reach a point that the lava's cooled so much that the viscosity has gone up so much that even if the lava is on a slope, it's too sticky to fall any further. And that's when the lava flow ends, right? The problem is the relationship between temperature and viscosity is really poorly known. So when the lava temperature, when you predict the lava temperature gets rather cool, the viscosity has just exploded. You're on some asymptotic limb of these viscosity temperature curves. And you can easily build lava flows that are 3 kilometers high because you just keep pouring lava into the cell, but it never reaches the condition to fall over because the viscosity is so high. So you just build mountains of lava on your DEM. It's crazy. I'll send some papers, read about it, but yeah, viscosity is very important. Estelle's thesis, yes, you can have that. There's a PDF of it. So why don't you if you can send me an email or something like that, I'll send you the PDF of her thesis. Do you also predict how lava behaves together with fuels? So do you mean when lava flows over vegetation? Is that question? Yes, that's that question. Sorry, I'm scrolling. Yeah, okay. So does lava, so this was the thing, if you look back at Daines, 1972 was one of the first theoretical papers about lava flow cooling. And he said, well, lava flows clearly cooled by radiation from the surface because you stand by them and you get red hot. And they clearly lose heat by convection. But he said they don't lose any heat by conduction through the base. And his argument was they've observed lava flowing over wet ground and they haven't seen steam explosions. So that was his justification for why they don't cool through the base, because if they did, they would flash water to steam and you would get explosions. That's not true, right? I mean, people have been harmed by explosions from lava flowing over wet ground. Sarah Fagent studies things called rootless cones in Iceland, which are formed by lava flows forming over wet ground and generating explosions. So lava does generate steam explosions when it flows over wet ground. So if you're talking about water is the fuel, then yeah, lava interacts with that fuel when it's in saturated ground that the lava flows over while it's being in place. Is there any deep learning based approach for lava analysis? Deep learning. So machine learning, well, you know, deep learning. Yeah, there is. So Kyle Anderson, who is at the USGS, he's done some work which is based on Monte Carlo type simulations. So inverting data sets generated by large simulations to work out the most likely progression of activity during a volcanic eruption. I guess that's the best example I can think of right now. So if you Google papers by Kyle Anderson and Paul Segal, you'll find some papers that they published within the last 5 years, which look into that. Okay, I'll write this question. Oh, sorry. So the guy who looked at this non-thermal, phonon-related emission prior to earthquakes was a guy called Friedemann Freund, and he was at the SETI Institute, but I haven't spoken to him for a decade. And he was kind of old. I mean, he may have retired. So thanks for staying up, everybody. You've done a good job. 3 hours is a long time. Actually, you're here for 6 hours, right?
Yes, 6 hours. This is the end of 12 hours. So it's been a fantastic. No, good job, everybody. Well, thank you all so much. Rob, thank you for a wonderful presentation. And so if you'd be willing to, yes, share your slides and some of those papers, then I can, or links to the papers, then I can kind of send them out to everybody. And okay. Thanks everyone for participating. Hope you enjoyed the online version of the 2020 IGAR Summer School.
Okay, so yeah, thanks a lot. Hope to see you sometime at a conference. Thanks, Ryan.
Oh yeah, very much.
I'll stop sharing, and I guess you end the meeting, right? Okay.
Yeah, I can end the meeting. Sure thing.
Thanks, everybody.
All right. Aloha. Take care.